So thank you for the introduction. Thanks for sticking around for this last Blitz talk here. So yes, the basic complex of a singular foliation. So this is a result I worked out for part of my thesis, which will soon be completed. So it has to do with singular foliations. So we'll begin with the definition of a singular foliation. Especially these days, the term could maybe be ambiguous, so I have to pin down what I mean. So for me, a singular foliation will be a partition of a manifold into leaves. And these, by leaf, will mean a connected and weakly embedded submanifold. So it's a partition of a manifold into these submanifolds. And there's a smoothness condition. So they need to fit together smoothly in the following sense. So it's a bit wordy, but I don't think it's too bad. For each point in the manifold, you can find a collection of vector fields. And these vector fields will locally span the tangent spaces to the leaves in the neighborhood. So in particular, they have to span the tangent space to the leaf at X, but also the leaves near X. And the reason this is a singular foliation, or potentially singular one, is that the vector fields can depend on the point X. So at different points, you might have lower dimensional leaves. Things can change around as you go through the manifold. Just a small comment on this weakly embedded assumption. It's a bit stronger than immersed. All it means is that or a consequence for us, is that the smooth structure on the leaves is unambiguous. It's completely determined by the leaf as a set and the ambient manifold structure. So I don't need to worry about equipping them with, I don't need to worry about the smooth structure on the leaves, specifying what it is. So give a definition. Here's an example. I started off with sort of one of the more general ways you can approach it. So if you have a Lie algebroid, then the integral submanifolds will assemble into a singular foliation. And more elementary examples can be deduced from this. So for instance, connected components of the orbits of a Lie group action will partition your manifold into a singular foliation. And also the symplectic leaves of a Poisson manifold will give a singular foliation. Okay, so what will we do with these? The question I'm sort of interested in is taking a singular foliation and looking at the leaf space. And well, what I'll do is I want to use what's called the diffeological structure on this leaf space to probe information about the transverse geometry. So here we're going to do a bit of a comparison, which we'll make precise in a second. So the leaf space will denote by M mod F. And like I said, it has a natural so-called diffeological structure. So I think Eugene mentioned diffeology briefly in his talk in the beginning. It's one of the various notions of generalized smooth structure we can put on a set. I don't want to dwell too much on the definition, so I just put it a bit vaguely here due to Chen and Suryao independently. So a diffeology will have a set, and we'll equip it with a set of maps from various Euclidean spaces or open subsets of Euclidean spaces into X. And these maps, which are called plots, will essentially determine what it means to be smooth. So if we have a function from a diffeological space X, we'll use the plots to define what it means for that function to be smooth, etc. In the footnote, I gave a brief description of these axioms that a collection of plots must satisfy. But again, I think I don't want to go too much into it because that's basically a talk on its own, or a 15-minute talk on its own. But the idea is that this leaf space has more structure than a topology. It has a diffeology. And so I can give a sort of vague formulation of the guiding question here. What aspects of the foliation sitting upstairs can we recover from the leaf space viewed as a diffeological space? And just to give a small motivation as to why this might make sense to ask, if we consider an orthogonal group acting on Rn for different n's, topologically, this quotient is just a half ray. And you can't tell the different half rays apart from the different dimensions that you started with. But the diffeological structure will be distinct for each of these. No two will be diffeomorphic. So I can say these are all diffeologically distinct. So there's a small reason to believe that this question is not hopeless. So we're going to approach this using basic complex. So first, downstairs on the leaf space itself, we have the following facts that we get from equipping it with the diffeology. So first, the quotient map is a smooth map, as it probably should be. Moreover, it's actually what's called a subduction, which is a diffeological version of submersion. Diffeological spaces always come equipped with a complex of differential forms. So that side of things works very well. There's nothing special about it being a quotient for these complex to exist. It's just the diffeological structure. And finally, the smooth quotient map gives a pullback of complexes of differential forms. So we have the forms on the, we have the forms on the leaf space, and they pull back to, right now it's just forms on the manifold. So this is the complex we'll look at downstairs, this omega m mod f. On the other hand, if we don't want to pass to the leaf space, we can stay with the foliation upstairs, and we can consider what's called the complex of basic forms, the second part of the title. This was first introduced by Reinhardt in '59. He was working with regular foliations at the time, but we can make the same definition for singular ones. So we'll call a differential form on the manifold basic if it is horizontal. So this interior derivative vanishing is called horizontal, and invariant. This Lie derivative vanishing is called invariant. And the x we take are those which are tangent to the foliation. If you have a foliation induced by a connected Lie group action, then invariant really just means invariance under the group action. But the horizontal condition just stays the way it is. And the notation, so we'll call this omega sub b m f. Okay. So now we have two complexes of differential forms. Morally, these basic forms should capture transverse geometry, but so should these forms on the quotient, since that is the leaf space itself. And we also have, conveniently, the pullback by the quotient. So we can ask, how does the pullback compare these two complexes? And we begin with this little lemma. Again, this is a consequence of general results in diffeology. So the pullback will restrict to a morphism of these complexes. So it will always go into basic forms, and it's also injective. Mm-hmm. Yeah. And so here we have injective, and then sort of the more formal version of the question I started with, we're going to specifically ask, when is it an isomorphism? And in particular, because of this earlier lemma, we're really asking, when is it onto? And that's the result that we have. So I did this maybe not a little, like a year ago or so. I guess it's 2 years now. Anyway, so we have the quotient will induce an isomorphism, or will be surjective, in the following three cases. So first, when f is regular. And I later found that this was also done by Hector Marcius Virgos and San Martin Carbon in 2009. And also, Yi Lin and Jiandong Yang also have an argument for this to be true in one of their recent preprints. So when f is a regular foliation, we are onto. More generally, though, we can now go to singular foliations, and the following condition suffices. So for each k, for each dimension of the leaves, look at all the leaves of that dimension, take the union, so it's a subset of the manifold, and require that this union is a submanifold. Now, I'm a bit general in what I mean by submanifold, but we can just take weakly embedded, or you can think embedded if you want. Most of the examples, it's an embedded submanifold. So if for each k, that union of leaves is a submanifold, then the pullback will be an isomorphism for that singular foliation. I'd like to call this stratified, the foliation is stratified by dimension or something, but I don't know that it's a stratification in the sense that word's usually used. That's why I don't write it here. And there's finally a third strange sort of condition that we can have, which is more general than the previous two. If you discard all the zero leaves from your manifold, that's what this m bigger than 0 is. And then you equip it with the foliation where you remove those zero leaves. And if the pullback is an isomorphism for that open subset of your manifold, then you can throw the zero leaves back in and it will remain an isomorphism. So somehow this question of when the pullback is an isomorphism, you can sprinkle in zero leaves however you like in any closed subset, and you'll remain an isomorphism if you started off as one. So I think it's a bit strange. You can make some strange examples with this. Okay, and yeah, IMRN is where this can appear. How much do I have? 5 minutes? Yeah, okay. I just wanted to give a little example of maybe to see how the diffeology sort of works or how you might use it. Consider the action of SLN on matrices by left multiplication. Then we want to sort of ask what are the basic forms for this foliation of the set of matrices. And we make the following diagram. So we split the determinant into the quotient map, and this map I just call it C. Then on the diffeology side, you can prove that this C induces an isomorphism on the complexes of differential forms from R to X. So the diffeology is here to make sense of that. And then the theorem comes in because we're in case 2. There's a sort of decomposition by dimension for this action. And so then we know that the quotient will give an isomorphism. And when you put these together, we can see that pulling back by the determinants gives you all the basic forms for this little example. Some more sophisticated examples, I guess I call them bigger. If we have a proper Lie groupoid, then linearization theorems tell us that we're in this decomposed by dimension case, this item 2. And this, you can use that fact to sort of reproduce work by Karchan and Watts on the same question in a more special case of a group acting properly, or more generally, a group whose identity component acts properly. So you can reproduce some earlier results with this. You can also say for a Riemannian singular foliation, results by Molino from the 80s tell you that these foliations are decomposed by dimension. So for each k, the union of k leaves is a submanifold. In fact, in that case, it's embedded. And I just want to make a little note that this second example actually subsumes the first one using Del Hoyo and Fernandez's linearization. You can say that every proper Lie groupoid induces a singular Riemannian foliation on the base. Its orbits are singular Riemannian foliation. So then the second one really gives you the first one. And finally, using this sort of stranger third part, where the zero leaves don't matter, so to speak, any one-dimensional singular foliation, the quotient will have this property of being an isomorphism when you pull back, because when you remove the zero leaves, you just have a regular one-dimensional foliation. So you can use this to generate a lot of examples where the quotient is an isomorphism. But of course, that's not all the singular foliations that could exist. So there's two sort of big, well, big for me, I guess, unknown questions here. So first, I don't know of an example where pi star is an isomorphism and it's not covered by this theorem. So I don't know of a singular foliation that's not one of those 3 types earlier where pi star is still an isomorphism. And bigger than that, I don't know if there's a counterexample. It would be, I think, interesting if there was one, what type of foliation that would look like. And I'm not sure. So in the last, I think I have 15 seconds, I guess the only item I'll highlight here is that to do this decomposed by dimension case, the fact requiring them to be submanifolds allows us to do induction. And sort of on each level for each k, you have a manifold with a foliation. So you use the fact you know it's an isomorphism when you have a foliation, and you can sort of piece it together to get the entire quotient as an isomorphism. So that's, yeah, thank you for your attention.